Okay, so in the previous video, we talked about the intuition behind overfitting, and now we are trying to quantify it with a more tangible sort of measure so that we can utilize that to analyze overfitting more. Now, going back to our example when we had a simple learner and we called it H2 because it was a simple hypothesis set. And let us assume that we denote the in-sample error for this simple learner as E in of H2. And we had a complex learner. We can denote the E in or the in-sample error for that using this expression. Now it's always the case that E in of H2 is going to be greater than or equal to E in of H10. We can tell that just by looking at some of the examples that we looked at, but also the intuition tells us that E in, like within the sample, if we are overfitting the data, and like the more complex learner is going to capture every aspect of the data essentially. So that's why this is always the case. Now, if this happens, so obviously E out, which mostly happens if this is the case, like this is a complex one, and so E out strictly greater than E out of the simple model, which is H2. If this happens, then basically we fit the data more than that was warranted, and that was the definition of overfitting. So now if this happened, we can define an overfit measure. So the overfit measure is going to be the difference between this E out of the complex model minus the E out of the simple model. Or maybe like think of these as the final hypotheses that you're going to come up with, maybe like G10 and G2. Right? Okay, so if you think about this like difference here, right? Higher the value of this measure of overfit, higher or greater is the overfit. Lower the value, less is the overfit. Okay, so having said that, we are going to look at an example rather an outcome of an experiment where we have tried to vary a few parameters, and based on that we've tried to come up with a general idea of what is essentially the relationship between the target function, the number of data points, and the noise or the measurement error, right? So what we did in that experiment was we controlled a few things. So these variables. The first one was the measurement error, that's noise. And just to like analyze, so noise is nothing but measurement error. And the second thing that we're trying to vary is the number of data points, which is n. And the third thing that we're trying to vary is the complexity of f. And by complexity here, we mean complexity of f, the degree polynomial q. So the degree of polynomial, which is q, and like how we are trying to vary the noise. This is like the variance in the measurement errors, so essentially sigma squared. Okay, so having said that, let's look at the outcome and let's try to kind of analyze what's going on in the results. So now let's focus on the picture on the left side, which is this one where we are trying to compare or sort of like have the x-axis that has like the number of data points n, and the y-axis has the noise level, which is sigma squared, as I said, the variance in the measurement errors. And the color code here signifies the level of overfit measure, so something that we just defined, right? So overfit is basically, if you look at the color code, red means higher overfit and blue means lower overfit, right? And so you have the scale here. So this is the scale. And we are only looking at the left-hand side. Okay, so what is happening here? As you can see, as the number of points is increasing, right? And here we have like the blue region here, and like the noise level is kind of moderate, and you have like this blue region up here. If you look at the noise side of things, regardless of the noise, with less number of data points, you will go into this like very high level of overfit, which means you should be using a simpler model. You can see that already from the picture. Because this model here will have a huge tendency of overfitting. So this is what this picture is telling us. as the number of data points go up and like this direction, essentially, overfitting goes down, right? And as noise goes up, overfitting goes up, which is the case here. You can see as the noise goes up, this area is like completely red. Even with a huge number of, like, to counter that effect, you will need like more data points, of course. But then, like, beyond this point, like even with 100 data points, you're still in the red region, right? So if you have a higher noise in the, like, you have a higher measurement error, a good choice is to use a simpler model, as you can tell. Right, and if like with moderate noise somewhere here and huge data points, huge number of data points, you can counter the impact of the noise. Okay, so that's what the model on the left hand side is telling us. Now we have another model on the right hand side, and what is it showing us? So the model on the left hand side, right hand, I mean this one, right, is a comparison. Like on the x-axis, we have again the number of data points, but on the y-axis, we don't have the noise, we have the target complexity, right? So what is this telling us? This is somewhat of a similar model, except that what we see here is like the model, if you look at the trends, they are similar, but the only difference here is that this is non-linear, right? So this again is revealing the target function complexity affects overfitting in a similar way as noise does. But the only difference here is that this is doing it non-linearly, which means as the target complexity goes up, the tendency to overfit goes higher. And then again, the recommendation in this region, prefer a simple model, right? Although this like is very counterintuitive if you don't look at this picture and you're just like thinking about it. The more complex the target function, we should have a more complex hypothesis to kind of fit that, like to come close to my target function. But remember one thing, we don't know the target function. All we have is the data, and the more you're trying to fit closer to the data, right? Because like you're really trying to fit to the data and not to the target function, and so there are higher chances of going astray as your complexity of the complexity of your hypothesis increases, right? Basically, if your model is more complex, you will tend to lie in this region. And of course, we can counter that impact by using a larger data set. So as the number of points increases here, you can see that we lie in the blue region, which is the good region where you don't overfit. And so, of course, that's another way of countering the impact of the target complexity. Okay, so having said that, we've talked a lot about noise. We've talked a lot about target function. Of course, I'm like reminding you, when we never get to see the target function, it is the data that we see, right? And so having said that, let us actually try to unify like both of these pictures in terms of like a more conceptual way of thinking about it. And let us talk about noise. Let us like kind of define what noise is. So in very basic terms, noise is that part of Y which we cannot model. So let me write it down. That part of Y which cannot be modeled. What does that mean? And why? So Y, by the way, I'm talking about this Y, is the observed value in the data, right? Whatever you have, the outcome value. That's what I mean by Y. Okay, so this is the basic definition of noise. And noise can come from two sources. So this has two sources. And what are those two sources? The first source is what we've been looking at until now, and that is known as the stochastic noise or the measurement error. So the first source is stochastic noise. Okay, let's try to understand what is this like stochastic noise, also called the measurement error. If you got confused with that term, it's nothing but the measurement error. Fine. Okay, so let's look at like in a regression setting where again I have like this one-dimensional x and y, and this is, let's say this is my target function f of x. And of course, you don't measure f of x. So if there is a point here, x1, and something corresponding on f of x is going to be f of x1. But let us say you measured this particular data point somewhere here. Measurement was there. So that is my observed value, which is y. So this is my, like what I observed in y, right? Whatever I'm calling it, y1 or whatever. So basically what I'm trying to say is that my observed y value is going to be my f of x plus some like extra whatever this is, and I'm denoting it by a small epsilon, right? What obviously we wanted was this, right? We wanted that f of x y should be equal to f of x to learn better, but this is what we observe, and this is what we have to live with, right? And so if we generate a target function, what we have to do here is that um, we have to, like, when deciding the model and when coming up with the final hypotheses, we'll have to deal with that. And so that's always there in my data, and my model is essentially going to be based off of that. So this is what is known as stochastic noise, right? Okay, so having said that, let's try to look at this example where we have some data. So obviously you never know the target function. So again, I'm repeating that. And let's say I have some data and with measurement errors, of course, because my target function is this. Let us assume this is my target function, and you can see because this data is has some stochastic noise. So we are unaware of the noise as well as we are unaware of the target function, right? And so we will model it with our hypotheses, whatever that hypothesis is. So let us assume that I came up with some order polynomial and I tried to capture this noise as much as I can, and I came up with this model because I was trying to fit in like every point that is there, right? So here what I'm trying to do is I'm trying to model the data with noise. And if I'm trying to model data with noise, there are higher chances of my model going astray. As you can tell with this simple example. Now, what is the key takeaway from this? You can see if we select a more complex hypothesis set, the chances of going astray are higher. So compared to a simple model, we tend to like go really haphazard in that sense. Now, we want to choose a simple hypothesis set, not because it has a greater chance of getting close to the target function, which is this, not because of that, but rather because it has a lower chance of going astray due to noise. And why is that? The reason is that noise cannot be modeled. And so a simpler model is definitely going to do better here. Let us look at this like quick summary of the stochastic noise. And so as I said, this is the stochastic noise as you can see in this picture. And obviously this part, the stochastic noise, cannot be modeled. One good illustration of that is, let's say this is my target function, right? But this is the data that I have. Now, as far as human beings are concerned, I can just like look at this picture and I can tell that this is an elephant. I would just easily disregard these points up there. But think of a learning algorithm, and let's say the data has like 100 of these pictures or 1,000 of these pictures, like maybe 100 pictures, right? And if in all of those pictures you have like a particular point here, that extra point up there, your learner or your learning algorithm is going to take notice of that, and that it's going to include that in your hypotheses, right? Which is why noise or the fluctuations or the measurement errors are dangerous, and we cannot really model them, and we really try to, when we try to include them in our hypotheses, there are higher chances of that hypothesis going astray and then eventually not generalizing well and all those issues. Okay, so having said that, there is another type of noise that occurs and that's quite common, and we will talk about that in the next video.